Okay, guys, now we're gonna be talking about work, power, and efficiency. Now, as we said, energy is the ability to do work. So, work is energy, and energy is work. Work is a scalar quantity, it's just like energy. So, work is defined by the force multiplied by the distance parallel to the force, which is the displacement. So, quick example, if you got a force of 5 newtons, it's going to push this box about 5 meters. So, the work done due to the 5 newton is going to be 5 times 5, which is 25 joules. All right. So, if you look at this example now, you have this box is being pushed by a 5 newton in this direction, and he's asking you to calculate the work done due to the 5 newton force. So you've got two distances here, you've got the 7 and you've got the 2. So the one we're going to choose is the 2 meters. So the work done is going to be is 5 multiplied by 2, that is 10 joules. That's for linear forces with linear distances. Now, how about you trying to go up the stairs holding a certain box, and I'm asking you to calculate the work done due to the weight or due to the gravity, right? So in other terms, this guy is gonna go up the stairs and you want to calculate the work done. So total his mass was 60 and had a box of 2 kilograms. So in this case, the main force is the weight of the box and the man. So that weight is about 62 multiplied by 10, so that is about 620 newtons. And he's going up. So what is the distance that is parallel to the force? That is the 10 meters. So simply calculate the work done is equal to the force multiplied by the distance. So the distance was 10 meters. So this gives you 6 kilojoule. Okay? This is in a very simple terms. Now, if we're going to talk about power, power is the rate of doing work. Power is the rate of doing work. So that energy or the work done could be kinetic, so half mv squared. It could be the gravitational, so mgh. Could be the work done, so also power is equal to force times distance divided by the time. That's another way of calculating power. So depending on the question. Also, you need to know that if the time that you do the work is small, then that means you've got a high power. So if you take a long time to do something, that means that you've got a low power. Now power differs. You've got electrical power, you've got mechanical power, also you've got brain power, right? So mechanical power is when you're trying to do some effort and so on, or you're trying to do a certain activity. That's for mechanical. Electrical is with the electrical devices. You're going to see that in electrical chapter in electricity. Or the brain power, it depends on how fast your brain works, right? So the faster you solve questions, the higher your brain power, and so on. Okay. Also, we talk about the efficiency. Now, efficiency is equal to the useful output divided by the total input times 100. Now, that output could be power over P in. That output could be energy as well, E out over E in. You could write this in E useful over E total, and so on. Now, there's something that you need to know. So, total is equal to useful plus wasted. That can work for power or for energy. Okay, you could be given the total and you could be given the wasted. You want to get the useful, so therefore the useful is going to be total minus wasted, or the other way around to get the wasted. Okay, a simple example for the idea of efficiency. You've got a power station at 100 kilowatts on normal weather. So on a hot sunny day, it's 25% less efficient. So calculate the efficiency of the power station. So you could get the power dissipated, which is 25,000 watts. So that is the wasted. So to get the useful is 25 minus the 25,000, you get 75. And therefore, the efficiency is equal to the useful divided by the total times 100. So that power station is 75% efficient on a hot sunny day. Okay. Also, you could be represented or given a Sankey diagram. Now, a Sankey diagram represents the flow of energy in a system. So on the left here, you've got the total energy, and here is you got the wasted energy, and here is the useful energy. So if you look at this this is, for example, a light bulb. So the light bulb is just presenting a 10 joules of efficiency, or sorry, 10 joules of useful energy, and 90 is wasted. So to calculate the efficiency in this case is going to be 10 divided by 100 multiplied by 10. So this bulb is about 10% efficient, okay? In Excel, you're going to be asked to draw this or scale it. It's pretty easy. But for now, this is what we're going to be covering in Cambridge, okay? Thank you for listening.